Right, 4:15, so we're good to go. And I need to apologize that for some reason today the green screen is having a kind of a dent, and that's why here there's something that is not how it's supposed to be. But let's not allow that to bother us. Lecture number 3, and today we're gonna do something practical, something that we're gonna learn to use the first analysis. So it's no longer about something that is hard to see the connection in real life. But instead, we're going to take a look like how is it we can run a kinematic analysis. So kinematic analysis is a kind of the main topic today. It may be possible that we don't have enough time to cover all the details related to kinematic analysis. And that will be okay because we can continue in that subject matter on Wednesday, next week, Wednesday. And then there's a comment that there is no lecture materials in Moodle under the third lecture. And yes, that is the case because today is our third lecture number 3. And this material that I'm about to cover today will be available in the Moodle database right after my lecture, or if not right after my lecture, then it will be available early tomorrow morning. So that's how it goes. So usually, because I'm not sure like how much I can cover during a 1 week, so that's why I'm not usually pasting the material to Moodle database in advance. But if you would like to familiarize yourself to material in advance or prior to the lecture, it is highly recommended to take a look at that Temeko material or take a look at the lecture note. So that lecture note is one-to-one copy what I'm about to explain you every single week. Okay, so good. So constraint equations, we will continue from that. Then we will discuss a little bit more about the number of degrees of freedom because we learned that concept already a week ago. And then something that is mathematically a little bit involving is a Jacobian matrix. So that's what's going to happen today. But prior to that, business as usual. And business as usual is a summary of the material we covered a week ago. So a week ago, we looked at the concept called Euler angles. And Euler angles is a procedure that is based on successive rotations. So the key is successive rotations. And what that means that once rotated coordinate system will be rotated twice, and then twice rotated coordinate system will be rotated third time. That's what it means. So we are moving, rotated system will be rotated again. That's what the successive is standing for. And then there is oh, I'm sorry, I was reading the chat a little bit incorrect way. So that's what the successive is standing for. And last week we concluded that one of the often used sequence of rotation is the one where we first introducing the rotation around z-axis. Well, let me back up a little bit. So first we're going to have two coordinate systems that are parallel in the very beginning. Then we're going to take a hold of the z-coordinate axis, and we're going to introduce the rotation this amount. And again, I'm really bad about this notation. So is this phi or psi? I'm not 100% sure about that. Anyway, so that is the amount of rotation we will first introduce. Then we will introduce second rotation, which will take a place around one's rotated coordinate system. So this is a key to understanding. So one's rotated coordinate system, all right? This time the rotation will take a place around x-axis, and amount of rotation is theta. And then finally we will do one more rotation, this time 2 times rotated coordinate system, and this time we're going to take a hold on coordinate axis z. All right. Each one of these rotations can be represented by using 3x3 rotation matrix. Now, this is something that you are almost familiar with, because if you look at how is this 3x3 rotation matrix, there is this submatrix that is identical the one we learned in a planar case. Planar is a 2-dimensional case. And then there is one extra column and one extra row. that is showing you where the rotation takes place. This obviously is a definition of Z coordinate axis. Same holds here. Second rotation will take place around the x-axis. So this obviously is a definition of x-axis. And one more rotation, which is exactly the same than the first one, except that, of course, the rotation parameter is different. Now, successive rotations in mathematics can be accounted by multiplying the matrices together. And once you do so, this is how the 3x3 rotation matrix look like. So let's get back to that after a little while, because here is an example. This is an example. Oh, hold on. So there's a really good comment in the chat window. Temeco course enrollment. Okay, this is something that I need to check it out. So you guys enrolled to Temeco, but you did not receive any feedback after that. All right, let me put that in my plate. So and I will get back to you next week at latest. I think that I need to get back to you a bit earlier than that. And then there's one more outstanding comment, and that's related to when is it you guys gonna get feedback regarding your weekly homework, and when the correct answers will be available. They will be available tomorrow, so I will guarantee you that. Okay, but let's practice these Euler angles a little bit. The first exercise that I would like to do to practice the Euler angles is that I would like to introduce the body rotation, 90 degrees. Thank you. Phi theta psi. Phi theta psi. I kind of promised to learn that, but I don't know what's wrong in my head, because I always say that, okay, this time I will make a serious effort to learn these notations, and then they stay in my head like an hour and then they disappear. But sure, we'll do my best. Okay, body rotates 90 degrees around the axis with a vector, which is provided here. Define the rotation matrix using Euler angles. Okay, so Euler angles is all about how to define these three parameters. Three parameters that we just learned what they are. They are phi, this guy, theta, this guy, and psi, this guy. So we just need to give up numerical values to these three parameters, and that's it. Then it's all about the substitution. Substitution in a way that once you know these three parameters, then you substitute that information to this 3x3 rotation matrix. So it's not complicated at all. No thinking whatsoever. All right. How is it we should select the parameters in this time? Because, obviously the vector where the rotation takes place is x-axis. And how much is a rotation? That's 90 degrees, which is p divided by 2. So it's simple. First rotation have to be 0. Second rotation have to be p divided by 2, because this is where the rotation takes place. Third rotation have to be 0. And once you substitute that information to your rotation matrix, what? Yeah, okay. Once you do this substitution, this is how the final solution is. Okay, what about the case that you wanted to introduce a rotation around y-axis? Remember that there is this question that I provided to you. I think that it was pretty much similar than the previous time, but this time it was said that the vector is 0, 1, 0. And that obviously is a definition of y-coordinate axis. Y-coordinate axis. So how is that we can introduce that? Because, if you look at these, again, these p, theta, and psi, none of them are related to y-coordinate axis. So none of them are related to this vector here. How is that we can solve this problem? Well, to solve this problem, we need to take a look at or kind of give us a high self-confidence, we need to take a look at the gyroscope. You know that in a gyroscope, you can put the gyros to any orientation you want in the space. And so if we're gonna follow that kind of like a gyroscope, we could do this in such the way that we're gonna introduce the first rotation such that coordinate axis x and y will change their place. So coordinate axis x and y will change their place. So I'm going to introduce a rotation that is amount of p divided by 2. That's 90 degrees. And what happens as a consequence of that is that the y-axis will be pointing this time. Excuse me, this have to be minus. Minus, I need to be going in another direction. So what's going to be the consequence of that? That means that the y-axis is pointing here, and x-axis is now pointing downwards. So now, x-axis is where the y-axis is where the x-axis used to be. So then we can introduce the amount of rotation we wanted to do. And I think if I remember correctly, it was like p divided by 6. All right. So then to compensate the first rotation, that was just to do to replace the angle or the axis direction, we need to compensate that. So that have to be the p divided by 2 to put it back. So that's how it goes. Happy? So this is an answer to you to solve that second task this week assignment. And then there's a question like why we have TV. Why we have 2 rotation on z-axis. Oh yeah, well yeah, that's just this is the sequence of rotation that is often used, and I think this is coming from the gyro. You can use another sequence of rotation if you want, so that's okay. So it's not really make any difference, and you can still put your gyroscope to any orientation in the space, so it's making no difference. But you kind of hit the spot because it's obvious to recognize that when using these 2 z-axis rotations, there's this possibility that these 2 rotations are not distinct. You cannot really differentiate what is what. So there is a high possibility to mixing things. That's something that is always a problem when you're using 3 rotational parameters. Always. No matter what set of parameters you want, what you select to use, or what sequence of rotation you use, you always have this problem. And I recommend you to take a look at something that is called, and I can send you a link for something that is called gimbal locking. It's a problem associated to Euler angles. And gimbal locking is something that is not the mechanical lock, but it indicates the fact that 2 rotations are not distinguished. So you cannot recognize what is what. Okay, so somebody's saying that I think that I made a mistake regarding the first rotation. So let me take a look. So first rotation, I should actually take a look at the material that I covered the last week. In this case, so x-axis, can it be positive 90 degrees rotation first, and then it's yeah, so I think I'm okay. It looked that this is now the left-hand side coordinate system. No, the right-hand side coordinate system. I need to double check this positive rotation order. I need to check that to you during the break. So don't take this too seriously, because there is a possibility that this one here is positive and this is negative. But that's the trick we're doing here. So we're switching the order of axis, and then we compensating that in the last rotation. But again, good comment, and I need to go back and verify my notations. Okay, tips for weekly assignments. Be careful with the radians and degrees whenever you're using trigonometric functions, which I'm sure is not a big problem to you. Make sure you're using correct submission box. That's another thing that you need to be careful with. And if you have any difficulties, please contact Jurat. And please do not submit it by emails. This is a little bit of headache, because we have, again, 150 something students, and if each of you are emailing me weekly homework, that's going to be pretty chaotic. All right, so then there's one more question about you can send email or similar. You can email to Suraj if you wanted to get help, but listen to me, I said that don't submit your homework by email. You can ask help, but don't submit your homework by email. So you can ask help by email as often you want, but you are not allowed to submit your weekly homework by email. All right? All right. Great. So let's continue then. Where is my pointer here? Now it's here. Okay, still a little bit summary what we discussed last week. This is going to be brief. So last week we looked at how is a definition of, or how is a velocity of a particle. And we concluded that the velocity consists of two components. So there's a translational velocity and the component that is associated to angular velocity. Then when you differentiate the velocity one more time with respect to time, then you can get that definition of acceleration of a particle. And this is how that looked like. Now this one is consisting of three components. So there is a translational acceleration, normal acceleration due to the rotation. So this is the one that is quadratically related to velocities. And then tangential acceleration, again, due to the rotation. So those are the three components. We will get back to this once we start discussing about inertia forces. Because, eventually what we're going to do is this. There's going to be mass multiplied by acceleration is equal than forces. This is our dynamics. But don't look at that in details yet because we have not discussed about the forces yet. But basically what this says that inertia forces, which is a mass multiplied by acceleration, is equal than external applied forces. All right, but we will get back to this after a week and a half. So then I still need to take a look at the chat window. Yeah, PDF is the format to do it. Can we use? Yeah, you can use, so if you want to use another sequence of rotation, that's okay too. But this is something that then you need to derive this rotation matrix by yourself, which is possible too. But to make it easier, I recommend you to follow what I just explained to you. Because if you're going to change the sequence of a rotation, then it means that, hold on, where is it? This guy. No. This guy is no longer as it is written here, because if you're going to change the order of rotation, then you need to modify this guy. Maybe painful, or maybe not. No comments. But again, either way, you kind of make your life easy if you're using a symbolic math tool. Okay, so we were this acceleration, and now final thing we learned last week was how is that you can compute the number of degrees of freedom. The number of degrees of freedom can be computed very simply. So you just take you just account the number of tenorized coordinates, which depends on how many bodies you have in a system. And then you accounted how many constraints you need. And then there's a different scenarios regarding the number of degrees of freedom. And these scenarios are introduced here. So number of degrees of freedom may be less than 0. System is unconstrained, so it cannot move. So that cannot move. So the number of degrees of freedom may be equal to 0. Equal to 0 is possible when you're introducing something that is called driven constraint. driven constraint, which is not like a revolute joint, which is kind of passive joint, but something that is active joint and introducing the motion. And the motion could be the one that is introducing the motion of this crankshaft or a motion of the piston. If I say that the piston have to follow sine, time, this kind of expression, that's considered as a driven constraint. Driven constraint. Now, driven constraint is something that it is a little bit hard to understand because it's not a force. It is predefined motion. So how can you use this predefined motion in a real life? Well, you cannot, because predefined motion is something that is not existing in a real life. They existing in a kinematic analysis, but in a real life, you cannot go to the nearest hardware store and say, yeah, I want to have two driven constraints, which are like sine time. They don't have it. This is something that is like a mathematical definition, mathematical thing that you cannot find in a real life, but it's handy when you're conducting the kinematic analysis. When does it make sense to run the kinematic analysis? Well, it makes sense to run the kinematic analysis to see if there is a problem of collision. If you see if somebody is capable to do a work, or if you wanted to define the workspace of a robotics and this kind of things, that's when you need the kinematic analysis. All right, the one more scenario here is that the number of degrees of freedom is positive, more than a 0, 1, or higher. Then you have a system that is dynamically driven. It's driven by forces or moments. And then the only way to solve the response of the system like that is to create the equation of motion and then solve that by using a numerical time integration schemes. And then there's a lot of comments, okay, about the submission. So you guys discuss about the submission and I will continue. Then different joints. How many constraint equations you need in case of different joints? So here are the different scenarios. This covers all the planar cases, all the two-dimensional cases. You may have a fixed joint, all right? So that takes off, or let me rephrase that. You need to have a 3 constraint equation to express fixed joint. Revolute joint, we learned that earlier. Revolute joint needs 2 constraint equations, all right? So we learned that already. Translational joint, which we briefly going to take a look at today, that too needs 2 constraint equations. And a primitive joint, that's the one that needs only 1 constraint equation, just one. Because think about it, what it's doing for you. Like this beam-like body can go up, can go down, and it can rotate. But it cannot move to global x direction. So that's the only limitation. All right, so those are the numbers you need. So let's take a look at let's practice these numbers, or let's practice these tables a little bit. Number of degrees of freedom. Okay, so let's compute it. Let's get started from this guy here. And the easiest way to do this is that we only are counting the bodies that are moving. So we can ignore bodies that are attached to ground, because those play no role in the dynamics. They don't move anywhere, so they will be standing no matter what. So let's just count how many moving bodies we have here. 1, 2, 3. So we have 3 moving bodies. How many generalized coordinates we need? Well, one body needs 3 generalized coordinates. 2 bodies need 6 generalized coordinates. 3 bodies needs 9 generalized coordinates. 9 generalized coordinates. Okay, how many constraints we have here? Well, we have here 1, 2, 3 revolute joints, right? So that's a number of generalized coordinates. 3 multiplied by 2, because each one of them needs 2 constraint equations. Okay, do we have anything else? We have translational joint here. So that's additional 2 constraints. What about this one here? There's a dot here. Is that a joint? No, that's not a joint. Just a dot to make you feel confused. So this is it. So this is all you need to know. Number of degrees of freedom, this gives you 8, is 1. This system can move one way only. So there's a one way that this system can move, 1 degree of freedom. All right. So let's take a look at the second one here. Now this is a bit confusing. This is a hydraulic cylinder, which is a piston and a cylinder. So let's take a look like how many moving bodies we first of all have here. 1, 2, 3, 4. All right. How many generalized coordinates we need if we have 4 moving bodies? 4 multiplied by 3, 12. 12 generalized coordinates. Okay, let's compute the number of joints. So we have here 1, 2, 3 revolute joints. So that's same that in the previous case. So it's 3 multiplied by 2. And then not showing here, but it's translational joints that are in the cylinder. So we have 2 translational joints. So let's compute it. 2 times 2. This is 6, this is 4, so it's 10. So the number of degrees of freedom, is 2. So there are 2 ways that the system can move. 2 ways are like this. So it can either go like this, or it can go like this. So it's a little hard to play this game by pens, but you got my reasoning. Okay. So is this clear? Do you know how to compute the number of degrees of freedom? I suppose that is clear. Okay, is it possible to change the assignment 1 anymore? No, it's already submitted. So, but no worries, because you know the guys that are checking the weekly homework are pleasant guys. They are not like me, like vicious person, but they are pleasant guys. So they are very flexible. So if they can see that there is an effort, they will give you points. So we don't really care if it is correct or not. That really is not important. But we want to see that you do something, you have an effort. That's what matters. Okay, let me put the Socrative on. So just here. So the first Socrative is actually on. And my first question is this. What is the number of degrees of freedom? So I have here system that have 2 moving bodies, 2 revolute joints, and 1 primitive joint. How you can do the math? You can do it similar way that I just did it for you in one slide back. Plus, you could take a look at this one here. Sorry, it's a mess. Let me make it a bit clearer. So you need to take a look at that there is a revolute joint. Revolute joint needs 2 constraint equation. And then there is a primitive joint. Primitive joint needs 1 constraint equation. All right, so let's go back to this assignment. First thing you need to do is that you need to identify how many moving bodies there is. Okay, once you know that realize that there are 2 moving bodies, listen to me. So once you realize that there are 2 moving bodies, then you need to do the math, like how many generalized coordinates are needed for 2 moving bodies. So if every body needs 3 generalized coordinates, so listen to me. So it's not that everybody needs love, but everybody needs 3 generalized coordinates. So that's how much the 1 body is needed. 2 body needs how much? All right. Then translational, revolute joints, they need 2 constraint equations, and primitive joint need 1. So that's your math. Okay, so then there's a question about if 2 translational constraints are removed, would the DOF decrease? I don't know. It depends on the case. So we need to take a look at that in my slides that are coming a bit later today. But anyway, so please enter your answer to Socrative. I see that it's look weird because it looked that I have 156 students. I don't believe that. That cannot be a correct number because I can see that there's a 68 views in my stream. So it sounds that that number in Socrative is clearly off. Okay. All right. So that was all my hints to you. So here's Socrative. Are you guys ready? Not yet ready. So let me put it off so you can see this one more time. And the game is on. How is the success rate? Is it going to be 100%? Yeah, primitive joint is one constraint equation. That's right. But how is the success rate? Primitive joint needs one constraint equation. Correct, correct. Yes. All right, so we have 65 answers, and I think that we got no more answers. 66 now. The game is on. Success rate. You guys are getting started with a fairly low number in my mind because it's like 80, 82, 78, 85, 91. I'm thinking 100%. Seriously, 100%. So I'm voting for 100%. And if it's going to be 100%, each of you that is in this game will get 1 extra point. How that sounds? Oh, Socrative is not working. Okay. All right. So the answer is this. Oh, 73 students. Big surprise. Like it's more than I have views in my stream. All right. The results are this. Okay. So it's nowhere near the 100%. Honestly, I'm disappointed. I'm disappointed because remember I just said that, 2 moving bodies. So how many generalized coordinates are needed if you have 2 moving bodies? If one body needs 3 generalized coordinates, two bodies need 6. All right. Then we have 1, 2 revolute joints, 2 multiplied by 2. And 1 primitive joint, plus 1. That's 5. 6 minus 5, 1. All right. Okay. Anyways, so listen to me now. Listen to me super, super carefully, because this in-class quiz will come back. I'm going to ask the same question after a little while. It's a little different configuration, but it's essentially the same system. So make sure that at that time you're able to answer that correctly. All right. Oh yeah. So is it so that you cannot see anything? Why you cannot see anything? Oh, the results. Oh, I saw it already. So here it is, 65. 65 on my disappointed face. All right. But that's okay, because the next time we'll do better. Okay, then some boring parts. Some boring naming things. We have different kind of names for different kind of constraints. Holonomic constraint is the one that we most often used. So holonomic constraint is like revolute joint. So most constraints fall under this category. So they can be expressed as an algebraic equation in terms of generalized coordinates. Yeah, that's what we've been practicing. We will practice this more. Then non-holonomic constraints are constraints that we are not going to cover in this course. Those are like rolling without slipping. Like if you want to model a bicycle or a vehicle, then it makes sense to learn how to use these non-holonomic constraints. They involve inequalities or generalized velocities. We are not going to cover that, but this is for your information. Scleronomic. are kinematic constraints. So they are time-independent constraints, and then rheonomic, sorry about that. Those are the driven constraints, the ones that are mentioned here earlier. So these are the names which are not important, but basically for your information level. All right, then what about in a spatial case, in three-dimensional space? This table here shows you how many degrees of, how many constraint equations you need in different type of joints. So these are the joint types shown here. And they're telling you like how many constraints are needed. Let's give you an example, like translational joint needs two constraint equation that eliminates the rotational degrees of freedom and two constraint equation for translation. That's a total of 5. So cylindrical joint, that's 2 plus 2, that's 4. Revolute joint is 5, and so on and so forth. You can also use something that I call primitive joint, which you can combine the joints pretty much however you want. This matrix here shows how are the different combination of primitive joints. These joints, these like conventional joints, you are not allowed to combine. You simply cannot do that. But these ones, you can combine it. Primitive joint, because the primitive joints are like piece of joints, so they are like components of joints. You can make any kind of configuration you want with help of primitive joints. Okay, so let's take a look at the door then. So door, and this is, by the way, now in a three-dimensional space, so this is a spatial case. So if this is a spatial body needs 6 generalized coordinates, so because it can move in 6 different ways. And now I'm gonna constrain this door to ground by using a revolute joint, which is located in the middle of the door. And like we learned in this slide here, revolute joint, which is this one here, needs 5 constraint equations. So 6 minus 5 is 1 degrees of freedom, right? But that's not the way that you see the doors being in a real life, because in a real life, there's not the 1 revolute joint, but more, 2, sometimes 3, sometimes 4. So what happens if we're gonna take a look at the door like the one that is showing here? All right, so still the same body, so it's 6 generalized coordinates. There's 1 revolute joint here, 1 revolute joint here. So that's a total of minus 10. 6 minus 10 is minus 4. Minus 4. That's clearly less than a 0. And a less than a 0 is if we go back to, where is it? This slide. Is this our constraint system. This is a system that cannot move. Have you ever seen door to move? Yeah, door actually can move. Door can be open or closed. What is this? Because based on the math we just did, door is over-constrained and cannot move. But in the real life, we have seen on evidence that the door can be closed and it can be open. So something is off here. So what is going on here? So am I doing a mistake in my math, or is there another kind of explanation for this? Well, there is another kind of explanation for this. And another kind of explanation is that, the number of degrees of freedom is computed in such the way that there's a number of generalized coordinates minus number of independent constraints. These constraints are redundant. They're constraining the same degrees of freedom, say they're acting in the same way. So they are not independent. So that's something that is called redundant constraint. And redundant constraint is something that most of the commercial software can automatically identify that there's a redundant constraint, and they can automatically eliminate it, or they may not. So this is not the good modeling policy not a good modeling policy to use redundant constraints. So try to avoid it as much as you can. Okay, then I'm not sure if I follow the chat explanation. I guess that I not try to understand that by my this time. I will allow you to ask those questions in a team session afterwards. And let me just move on. Okay, so redundant constraint. This is, by the way, copy paste from the lecture material. So this says independent. This is pretty much what I just repeated or mentioned to you. Independent constraints. Now, in a redundant constraint, so it's not independent. It will be the same case that you have here two revolute joints. So they are dependent. So they are not independent constraint. This is something that I'm referring back to one of the questions in a chat window, because they was asking a question about, okay, so how did is this taking off to translational joint, what that means. So if those joints are not independent, then it makes no difference. So that's my answer to you. Okay, so then in a three-dimensional space in general, it's a bit of the problematic and bit of the headache to make sure that there is no redundant constraint. Let me demonstrate that to you by showing you a 4-bar mechanism. In 4-bar mechanism, we have 1, 2, 3 moving bodies, meaning that we have 3 multiplied by 6 generalized coordinates, so that's going to be 18. And then we have here 1, 2, 3, 4 constraint equations, revolute joint. 4 multiplied by 5, that's going to be minus 20. So 18 minus 20 is minus 2. So this 2 is a redundant system. And the redundant system, because the motion of the plate is too constrained. So to get rid of this joint could be replaced by a primitive joint, or you can use a cylindrical joint in some other location. So those are the ways to make this system to have 1 degree of freedom. So just a demonstration to you. Okay, let's practice a little bit more about the constraints. So here's an example. This is an example of I guess that is a pendulum some kind. And the pendulum some kind which consists of a one body only. So there's a one moving body, beam-like body. And the beam-like body is constrained to ground by 2 primitive joints. All right. These primitive joints are located in such the way that this one here, which is named as a Q, is amount of D off from the global x-axis, or origin of the global x-axis. And then there is a primitive joint called P that is amount of, what is this, E from the 0 of the y-axis. So those are the primitive joints. All right, so how is that we can introduce the constraints of this system? Well, surprisingly, we can use this equation that we are very much familiar with. And in this equation, we're simply setting the limitations based on these configurations. So it's pretty straightforward. And always make sure that you're always using this equation. No other means are allowed. Even though that you can see that maybe there's a shortcut. Don't take a shortcut. Always follow this equation. All right, so it means that we're going to first get started here in origin of the global coordinate system. We're traveling to origin of the body reference coordinate system. And then with help of a U-bar, we're going to one of the ends of the beam-like body. And there we're going to introduce the constraint. Motion limitations such that this point cannot move to this direction, and this point cannot move to that direction. That's what it is. Let's make it happen. Let's make it happen. So let's first constrain this point O. This point here. Okay, so let's go to this point using the vehicle we learned already. So this is our vehicle. So this is the only way we can travel to this point where the constraint is located at. Okay, so it means that we're first going to travel, again, we're going to first travel the origin of the body reference coordinate system, this guy. Then we take account the orientation of body reference coordinate system, this guy. And then we're going to move to where the constraint is located with help of vector U bar, this guy. And here it is expressed by using vectors and matrices. So this is a vector that takes us the origin of the body reference coordinate system. This is 2 by 2 rotation matrix. Vector U bar is the only one that is a little difficult, but not so difficult eventually, because if you look at this carefully, x-axis is pointing downwards. So we need to travel along with the x-axis to reach this location. All right. So that's the vector U bar. And then the constraint. All right, so this telling that, okay, this is where the point is located at. Now we want to say that, okay, this point cannot move in the global x direction. So actually the distance from the origin of the global x-axis have to be d. So we set this to be d. This can be whatever it wants. So it can go up and down. This is our constraint. Oh, excuse me, once you do the math, this is our constraint. Okay. So what about this one? Well, redo the whole thing. So it goes like this. We're gonna we'll make a use of this equation again. So we're traveling here, the origin of the body reference coordinate system. We take orientation into account. We're using the U bar to go this point here. And then we're gonna say, okay, this point can do whatever it wants, but it cannot move anywhere else than except the E in a global Y direction, right? So everything is very mechanical. This is business as usual. The vector U bar is only slightly difficult thing, but again, look at this. The x-axis is pointing this direction. So once you're here, you need to move to minus L divided by 2 to reach this location. And that's your final destination. And then you do the math, and this is your second constraint. All right. What's the number of degrees of freedom? There's one moving body. Every body needs 3 generalized coordinates. 2 constraint equations. So 1 degree of freedom. 1 degree of freedom. Okay. What follows is in-class quiz, and is related to these constraints. And think about what the constraints are doing for you. Think about what they are doing. So they are coupling. They are combining generalized coordinates. So they are saying that the generalized coordinates cannot move as they want, but they have to follow the certain constraint. That's what they're essentially doing for you. So is there? So now I'm not sure. Is there any changes? Sure, not sure what that is. So I'm simply gonna skip that question and showing your next in-class quiz. This one. Constraint equation. What's the purpose of constraint equation? Let me read these options to you, and let me give you a little bit of hints while I'm reading those options to you. The Socrative is on. Don't enter your answer yet. But think about that we have not discussed anything about inertia or masses. Then think about what I just said about the rotational particle. That's something that we discussed 2 weeks back. Channels. Are there any? Is there any challenge for channels for this? Yes. So I think that I'm not sure. I think that there are some additional YouTube material. I need to get back to that in a team session afterwards. Okay, but constraint equation. What's the purpose? What's the essence of constraint equations? Option number 1, interconnects. connects, combines, generates coordinates, defines center of the mass, define physical dimension of the body, define a particle rotation. And the game is on. So go ahead and enter your answer. And I see that it's already this late, so I don't know what happened. So it's already 5 past 5. Anyways, game is on, so you can put your guess about the success rate. Oh, the last time the success rate was actually 65. So let me see if there's any winners in the success rate competition. Sorry that I missed that. We do. Yeah, 64, which big surprise. I thought that with that low number, you cannot be a winner. But yeah, there is a winner. Okay. And the game is on. And now there's my man. There's my man with a 100%. That would be nice. That would be nice. But the reality, maybe a bit different, I think. I think that it is a bit different. Okay, so I have 60, let me see. No, yeah, exactly 61 answers, 62 answers. So momentarily I'm able to show you the success rate. And then let me see how much more material I would like to cover today. There is my slides. Okay, I think there's some good stuff coming ahead. All right. 71 answers. I think it's roughly the same amount of answers that we got last time. So let me close the game. So here it is. Success rate is 82. 82. So you guys are getting better. You're obviously getting much stronger further we go in the lecture today. So let me see if we have a winner. So we have 80, but do we have somebody that really hit the spot? No, we don't have that, but it's close. 80 is oh, yeah, we do. We have 80. We have 82. Good work. So we do have a winner. Nice. All right. Let me take this off. Let me continue then. All right. Then comes a bit complicated thing. Because this is a very complicated, but on the other hand, very mechanical too. I'm going to speed up a bit and I'm not going to really look at this in a super details. So this is where I would like to introduce you a translational joint. And translational joint is something that is here to combine this beam-like body, which is called body A, and the box-like body, that is body B. So so how to make it happen? So how to introduce the constraints such that the box-like body can slide along the beam-like body? That's going to be our challenge next. All right. You already know that this needs 2 constraint quiz, and I'm sorry that I'm blocking the view. These slides keep on changing their position for the reason that is unclear to me. I will make a short changing in my setup. Here you go. So it should be better now. Okay. So the first constraint is very straightforward because in a translational joint, the bodies cannot rotate relatively with respect to each other. So it means that the first constraint equation can be set simply like theta related to body 1 minus theta related to body B minus constant, which could be 0 constant. If there's no angle difference initially, have to be equal to 0. And how did you show in this configuration? C this one here is actually 0, because I can see that, the body reference coordinate system are having the same orientation in the beginning. So that's my first constraint. Second constraint is the one that I warned you already. So that's the one that is this painful. Hold on. I'm in the wrong window, so I'm here. Okay. That's the one that is a little bit painful. And in order to introduce that, I'm gonna select a couple points here. So I'm gonna select where the origin of the body reference coordinate system is located at, and then the point P here. And the point P here is roughly a middle of the translational joint. And then the one more point. Okay, so there is somebody that don't know how to answer the in-class quizzes. So you just take a look at you enter into the system by using your student ID number, and you can find that in the CISO. Okay, anyways, so then the one more point that is needed here is the one that is perpendicular with respect to this line here. So the one that is having 90 degrees angle with respect to this line here. And now once I select these 2 points, then I can introduce vectors correspondingly. And these vectors will be the ones that are, let me see if they are not necessarily clearly shown here, but there is a KAB that connects this point and this point, and HB. Those are the vectors that I need. These are now the better picture about the configuration that I'm doing here. So basically, let's get started by selecting these 2 points. It could be 3 points. This one, and this one. And then based on that selection, you're creating these vectors, K, A, B, and H. Now, once you're done with that, then you're setting these vectors to be perpendicular with respect to each other. And that's perpendicular is a mathematical condition that allows you to express that fact that they cannot move relatively with respect to each other other than sliding. So that's a sliding constraint. Sorry that I'm a bit unclear in this matter, but end of the day, what matters is that you're selecting these 3 points, you're selecting these 2 vectors correspondingly, and that's it. And then you just set this perpendicular condition. Perpendicular condition we're going to take a look at in a second. All right, so this AB is first body in a point O, second body in a point P. So then you do this expression by using the mathematics that you are very much familiar with. I'm not going to take a look at the details here, but you know how to do it. This is your KAB vector. Your HB vector will be within the body B, and it can be expressed as it is shown here. So it's again defining this point here first and then this point here. All right. So this is how you can express the HB, and this is how you express this KAB. All right, now you finally, and sorry that I'm having this good speed, but I'm sure you are not enjoying this too much. So let me just speed up a bit. Now you have these 2 vectors, and once you have these 2 vectors, then you're setting this perpendicular condition. A perpendicular condition is that you multiply or you take a dot product of these 2 vectors, and the dot product of these 2 vectors have to be equal to 0. That's the mathematical definition of perpendicular condition. All right. So now what I'm doing here is that I'm expressing these vectors in details, like shown here. So this is HB, KAB, similar way. This is finally how the vector KAB can be written. And then I'm setting that perpendicular condition. And when I'm using the configuration as shown in this figure here, my second constraint equation will be a scalar component. Okay. What we need to learn from this? We need to learn the facts, the following facts. So we need to set the 3 points. Based on these 3 points, we can set 2 vectors. And the perpendicular condition of the 2 vectors is that dot product of vectors have to be equal to 0. And that's scalar too. It's scalar, eventually scalar component. So once you do the math, you will get the second constraint equation. That's the one that is written here. End of the story. End of the story then. Okay. Let's look at this planetary system and let's try to create a constraint equation for this system zone here. So what I have here is two moving bodies, two moving bodies. Then I have here 1, 2 revolute joints, and then I have one more joint which is a primitive joint. Okay, that's my configuration. So I'm going to create the constraint equation for this system. But prior to that, let me ask you this. What is the number of degrees of freedom of this system? Don't answer yet. Hold on. Don't answer that yet because I need to put it on. And even before you enter the answer, let's take a look at something that is interesting. What's the difference between this particular example and the example we looked 15 minutes back? What is the difference in terms of number of degrees of freedom? To answer that question, you need to take a look, like how many bodies you have, how many revolute joints you have, how many primitive joints you have. And once you're done with that, then you can finally do the math. Options are, again, 0 degrees of freedom, 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom. Okay. Just checking how is that I'm doing in stream-wise. It looks okay. All right. 5 answers already. And the success rate competition is on. So let me see. 23 answers. So I'm going to wait a little while and then I'm going to close it. Okay, and the success rate competition is on. The previous winner is saying this time it's going to be 87. Yeah, it could be, but what about 100%? And here's 100%, another 100%, so it's getting way better. Way better, but is it 100%? We're going to learn that in a couple of minutes, less than a minute, within a minute, let's say, this way. Oh, look at that. We have so many 100%, so it's amazing. It's really amazing. Okay. But is it 100%? We'll see that. 61 answers. So I'm still expecting a couple more and then we're good to go. And we're going to take a look like how is it we can introduce the constraint for this system, and then we're going to move on to kinematic analysis. Oh, look at that. So there's so many 100% guesses that it's unbelievable. So there's a high tension here. So it's a high possibility that we actually going to hit the spot. And that's 100%. 67 answers. So I'm going to close the game momentarily. I think I will close the game right now. Here's a Socrative. All right. Okay, I have good news. We are getting better. We are getting better all the time. So this time is 88. Success rate is 88, but not 100%. Not 100%. Correct answer is 1 degree of freedom. And why it is 1 degree of freedom? Let's take a look at that next. All right. First of all, what's the difference between these two configurations? No difference. The only, that there is a difference, of course, that the primitive joint is not in the same direction, but degrees of freedom wise, it makes no difference. So it's all the time same. So it's not making any difference really. Okay, so now let's start by computing how many moving bodies we have. So we have 2 moving bodies, so that's 6 generalized coordinates. Then there's one revolute joint here, another revolute joint here, so that's 2 multiplied by 2, that's 4, and then there's a primitive joint here, plus 1. So that's 5 constraint equations, that's 1 degree of freedom. So it's a 1 degree of freedom system. Okay, and then I will take a look at the winners from this success rate competition a bit later. So I'm not gonna take a look at that right now. All right. So how these constraints? How is that we can introduce these constraints then? Okay. So it's simple business. So we can follow make a use of this equation. All right. It means that even though that the first revolution is located here in origin, we cannot make a shortcut and stay here. We always have to start from the origin of the global coordinate system. We need to go to origin of the body reference coordinate system, take the orientation into account, and come back with help of U-bar. All right. That's what we're going to do here as well. So here's a translation, here's a rotation, and this is the vector U-bar that takes you back from the origin of the body reference coordinate system, the origin of the global coordinate system. Okay, how much this can move, how far this is off from the global coordinate system. It is not off at all because it's origin of the global coordinate system, so the constraints are 0, 0. It's exactly where the global coordinate system is located at. All right. Second one is something we practiced a week ago. So we define this point here by using this body here. We redo the same by using a body B. And here it goes. So first we're gonna travel to origin of the first body reference coordinate system. We take orientation into account. We take a use of vector U bar. We redo the whole thing, but this time using body B, translation, rotation, vector U bar. Once I do the math and moving everything to left-hand side of the equation, it gives me 2 additional constraints. So it's a 4 constraint in total. All right. Final is my primitive joint. Primitive joint that is nicely along with the global x-axis. So again, I'm going to use this equation to take myself from here to where the primitive joint is located at. So first translation, then orientation, then vector U bar. And now I'm going to set this y direction to be equal to 0. So this is set to be 0. And once I do the math, that's my 5th constraint equation. 5 constraint equations, 3 generalized coordinates. So that's my system. Okay. All right. So let me see. Let me check for some reason my phone is really lacking. Okay. Great. Jacobian matrix and kinematic analysis. That's what follows next. And my slides are again jump a bit, but I guess that they're coming back, and here they are coming back. Okay, kinematic analysis. First of all, you can conduct the kinematic analysis only if the number of degrees of freedom is 0. And how is that you can make that to be 0? Well, you can make that to be 0 by using conventional constraints and driven constraints. And driven constraints, like mentioned earlier, can be considered and can be interpreted to be a predefined motion. So predefined motion, which is not based on the force, but it's just result of your imaginary. So it's something that you think that, okay, I want to introduce a motion like this, and you express in that motion mathematically. That's what it is about, nothing else. Okay, where you can use is a kinematic analysis. So you can use that in defining the workspace, because you can reach out the structure arms and see, okay, how far off it can go. You can use that in a collision analysis. You can use that in a preliminary studies of the mechanical structure, just to see if they can move with respect to each other, or if there's something like a locking or something that is bothering you. So that's where you can use a kinematic analysis. But again, requirements to conduct that is that the number of degrees of freedom need to be 0. That means that n is equal than nc. N is a number of generalized coordinates. NC is a number of constraint equations. Another way to interpret this, that the number of generalized coordinates, which are kind of like our unknowns, those are the one that defines our configuration, which having the same number than equations that can solve the unknowns. All right. So if we have one, let me describe hypothetical system, so which is a pendulum. Sorry about the low quality drawing, but the pendulum initially have 1 degree of freedom because of the one body, 3 generalized coordinates, because the revolute joint, 2 constraint equations, so that's 1. So now we're gonna delete or eliminate this 1 degree of freedom by saying that, okay, this pendulum cannot move as it wants, or cannot move because of the gravity, but it have to be following something that predefined motion, and the predefined motion could be sine time. Then that's a driven constraint, so that's a predefined motion. So then the number of degrees of freedom is 0, and then you can analyze how it actually moves. This is a very simple example, but you can use that in a way more complicated examples too. So it means that I have 3 constraint equations, 3 unknowns, and just using the information of constraint equation, I can solve the response. I need no further information to make it happen. And that's exactly what the kinematic analysis is about. All right. What are the steps you need to take in kinematic analysis? First of all, you need to solve position analysis, meaning that you have this, like in the previous case of this pendulum, you have first constraint equation, which is something, then you have second constraint equation, which is equal to something, and then the third, which is this driven constraint equation, which is something. Using this set of equations, you need to solve generalized coordinates. And that's the first task you need to do. That's the position level analysis. Position level analysis, and it says here that it's challenging. It's a little bit challenging, that's true. And it is based on iterative process, because basically we're facing the situation that we have nonlinear algebraic equations that need to be solved. And unknowns are not exclusively expressed, but they are hidden inside of these equations, because these constraints are function of generalized coordinates, so they are not explicitly expressed, but they're hidden there. And that's what makes that a little bit of challenging. So we're going to use a iterative process to solve it. Then the velocity analysis, that's going to be simple. That's very simple. So it's a matter of a substitution, not difficult at all. And then there's an acceleration analysis, which is okay. So it's not super easy, but it's not overly complicated either. So this says that to take care of all these stages, one step is critical, and this is to write down the constraint equations. That's you have to have. If you don't have that, forget about the kinematic analysis. It's not going to work out for you. This says that once you have a constraint, then the rest is a boilerplate. Yeah, kind of, but still, this position analysis, which is based on the iterative process, is a little bit of headache. Okay, so that's big concept. That's a big picture. What about the details? How it goes in details? Okay. Well, here's another observation which I think it is important. So in kinematic analysis, we don't speak about the forces, and we have not speak about the forces yet. We will get back to that once we discuss about the dynamics. But so far, it's all about how to define the coordinates and how to express the configurations. So that's what we've been discussing so far. So that's something that is good to keep in mind. And here's something that I have repeated more than a million times already. So the number of degrees of freedom must be equal to 0. And then solution is this set of constraint equations. That's all you need. Now the difficult thing is that if you have this set of nonlinear algebraic equations, how is that you can solve them? Well, the very often used procedure is based on Newton-Raphson iterative process. And in the Newton-Raphson iterative process, it goes such the way that you are not capable to solve directly what is a solution of this equation. Or you kind of want to solve this with a given time. And you need to do that in an iterative way. And once you do that in an iterative way, you need to compute something that is called Newton difference. The Newton difference is this guy here, which is a delta Q. It is not solution, but is a map to you. It tells you where the solution is located. Once you take a map and you follow the map, you will find a solution. But you need to make, or it's possible that you need to make several steps to find the solution. So what happens is that this telling you how is that you should change your generalized coordinates, that your configuration, to get a better estimate about the solution. So you can do this once, you can get rough estimation. You can do this twice, you get a little better estimation, and you keep on doing this, and you get better and better estimation until you're happy. Okay. Now, this is how it goes. This one here looking pretty bad. So this is a partial operation. So it's a partial C, which is a partial constraint equation, partial Q. And the Q again is a generalized coordinates. This is what we're going to look in the details. And then this guy here is a constraint equation minus in a sign. Where this Newton-Raphson is coming from, well, you can derive that by using this. You can introduce this small displacement change to your constraints, like shown here. And then you can use a little bit of your mathematical skills. You can express this using a Taylor series, where this residual, this guy here, is expressed as it is shown here. So this is where this is coming from. So first we have the constraint equation, then constraint equation differentiated once with respect to generalized coordinates multiplied by delta Q, and then higher and higher order terms, which I'm sure you guessed already. We really don't care about these higher order terms. We're going to simply ignore them. Okay, so let me see where we are at. So we're here. So using this procedure, we can express this Taylor series as it is shown here. And we can set this to be equal to 0. And this is our solution. Then we can solve this guy here finally. And to solve this guy, we need to take this partial operation, which is a matrix eventually. We have to convert that and then multiply that by a vector of constraint equations. All right, I'm sure this sounds bad. It's not that bad. It's okay. So it's not that difficult that it might sound like. But there is something we need to first take a look in details. This is this guy here, which is a partial C, partial Q, which is called Jacobian matrix. Basically, we are differentiating our constraints with respect to generalized coordinates, and that's called Jacobian matrix. Jacobian matrix is full of partial operation because it's a matrix that you can compute it as it is shown here. So first row of Jacobian matrix, you can take it or you can obtain it by taking your first constraint equation and then differentiating your first constraint equation with respect to all the generalized coordinates. So if you have let me see, if you have 3 generalized coordinates, then the number of columns is 3. So that's where the first row is coming from. Second row, you take your second constraint equation and you differentiate that too with respect to your generalized coordinates. And then you move on until you hit your last constraint equation, and that too you differentiated with respect to your generalized coordinates. That's how it goes. Let's practice. Here, this is, by the way, now it becomes obvious that you desperately need a symbolic math tool. You desperately need that. Okay. This guy we looked earlier, just a couple slides back. This beam-like body, which is constrained by using two primitive joints, one here, second one here. All right. So we concluded that the constraint equations can be written as it is shown here. And what we're going to do next is that we will compute the Jacobian of the system. All right, so the constraint equations is the one piece of information needed to make it happen, but we need another piece of information. And another piece of information is very straightforward. So we need to know what are the generalized coordinates, what are the unknowns, what are the things that we are after in this whole thing. Well, the generalized coordinates, because we only have one moving body, are Rx, Ry, and angle theta. Those are our generalized coordinates. And now what follows is that we need to introduce, or we need to conduct a good number of partial operations. First, we're going to take the first constraint equation and we're going to differentiate that with respect to first generalized coordinates, Rx. Okay, let's do it. Here's the first constraint equation. Rx is mentioned here, but it's just a one linear component. So once I differentiate this with respect to Rx, it's going to be 1. All right. Then I will take this first constraint equation again. And this time I'm going to differentiate that with respect to Ry. Ry is not mentioned here anywhere, so it's going to be 0 because it's not mentioned. Then I'm going to differentiate this equation, but this time with respect to angle theta. Here's angle theta. This is where the angle theta is located at. So once I do that differentiation, I'm going to get minus L divided by 2 multiplied by sine theta. All right. Then what follows is second constraint equation. The first that is differentiated with respect to x. X is not here, so it's going to be 0. Then with respect to Ry, there's equal to 1. And then angle theta, so it's going to be minus L divided by 2 cosine theta. That's it. That's your Jacobian. What the Jacobian is telling you? Well, it tells you very critical information about your system. It tells you, first of all, how many... Okay, let me see if this goes. It goes okay. It tells you how many generalized coordinates you have in a system. So that's number of columns. It tells you how many constraint equations you have in a system. That's number of rows. And remember, what we need to do in a kinematic analysis, we need to invert Jacobian matrix. And you know from the mathematics that you can only invert the matrix if it is square in shape. So we cannot invert this matrix because obviously not the square in the shape. So we have to have one more constraint equation, otherwise this is not going to work out. But what, hear me now, because the next what follows is one more in-class quiz. So what the Jacobian matrix is telling you? It's telling you the number of generalized coordinates, number of constraint equations. Is it exactly the information we use to compute the number of degrees of freedom? Yes, it is. It's exactly that same information. Jacobian matrix tells you what? Physical dimension of a body, color of the body, number of degrees of freedom, rotation of a particle. Those are the 4 choices, and the in-class quiz is on. Hold on, it's not yet on. I lost my, it's on. Okay, so then there is a y. Okay, so I think that it is, there's a question which I need to back up. Can I leave Socrative on? Now I lost my pointer. Here. So the question is this one. When you're differentiating cosine, d cosine is minus sine. D sine, this is differentiation. Differentiation of sine is cosine. So that's where it's coming from. It's coming from the differentiation rules. Okay. 100% 4 times. That would be great. That would be really great. I don't believe that by myself. I definitely don't believe that. It would be nice to have 100%. Definitely would be great to have 100%. But I don't believe that by myself. This is the last in-class quiz of the day. We, by the way, otherwise too, we almost done for today. So it's just a couple of minutes left. We have 67 answers already, 70 answers already, so 71. So I'm good to take a look at the results of in-class quizzes. So here it is. And the game is on, so there's a number of answers or votes for 100%. I myself thinking 55. That's my guess. All right, so who is closest? Ready? Here it goes. Oh, I was wrong. So I was seriously wrong here. So it's okay, almost 89%. 89%. Not bad at all. Not bad at all, because this is not the simple thing. And let me see what are if we got a winner here. Oh, there's quite a bit of answers here this time, but not. I think we have no winner. Or do we? Not as far as I can see. There's 80, 81, but not. There's 80. 80 is pretty close. That can be called as a winner. Okay, let me check this. I'll hide this one. Jacobian matrix tells you, it's not telling you anything about the physical dimension of a body. So that's something that you cannot define based on the Jacobian matrix. Why is that? Because joints can be located anywhere you want in a body. So they are not necessarily in a corner or one end of a beam-like body, but they can be anywhere you want, anywhere they want. So I'm just checking what is it you guys are saying in the chat window. Not sure if I follow you. It's a kind of hard to focus on the explanation and same time looking at that chat window. But anyways, so it's not the dimension of physical dimension of a body. Color of the body has nothing to do with this, and no one, which is great, no one is voting for that option. So that's something that makes me happy. It tells you the number of degrees of freedom, because look what I just explained to you. I explained that you cannot count the number of generalized coordinates, number of constraint equations, and that's an information you need to compute the number of degrees of freedom. But then some bad news. So 5% of you voted for rotation of a particle. That's big disappointment. Oh, okay. So you guys that's what you're saying. So you're saying that this one student, which I'm not going to mention the name here, got it right. Did he really? Okay. Yeah, you're right about that. You're right about that. Okay. Rotational particle is something like a Santa Claus. No, it's not. This is something that is a product of your imagination. So it's not something you can find in a real life. Why? Remember, because the particle is so tiny, so small that it don't have a rotational degrees of freedom. That's what we agreed in the very beginning. That's a fundamental. So the particle don't do the rotation. So you don't see it and you don't take that into account. So none of the stuff that I'm offering here, the never ever rotation of a particle is a correct answer. Never ever. And that, by the way, comes over and over again. So I'm going to keep on introducing that option to you. Make sure that you're not voting the rotation of a particle. Okay. And that's it. That's pretty much it. That's what I would like to explain today. So we spent hour and a half. Yeah, I would like to get back to the details or algorithm that is needed in a kinematic analysis, but we're going to save this for next week, Wednesday, and then eventually we're going to conduct the kinematic analysis, real kinematic analysis. So that's going to be your first computational analysis. It's going to be exciting. I'm sure, at least in the previous years, there have been a lot of high emotions, people crying and being really happy, laughing, crying, all that, because you learn to conduct the kinematic analysis. So stay tuned. See me on next week, Wednesday. With that, I'm going to close the streaming and introduce you or invite you to team session that is about to get started. So again, use a link that is available in a uh, Moodle messages or announcement or whatever they are called, and see me soon in Teams. Take it easy.